All right, cool. Hi, everyone. I'm Feiyang from the Tenzi lab. We work at computational oncology. Today I'll be telling you about OncoState, a project where we learn patient states from clinical timelines, but it's also the exciting time of the year where we have new faces. So before I talk about my project, let me talk about my lab. In the Tenzi lab, we develop machine learning methods for cancer biology and cancer therapy. There's a line of work focusing on cell and tissue level readouts, such as metabolites, spatial biology, where we work on lots of fancy methods, flow matching and diffusion for solving the technical issues of spatial transcriptomics so that you can do higher level cell-cell interaction inference. You've just heard Jess talk about her project on mutant kinase activity, which extends into the second arm of the lab, where we do adaptive large-scale drug screens to answer the question of how to treat biological conditions in the context of cancer. And a highlight project is an ongoing effort where we have AI-driven combination drug screens together with spatial profiling of tissue samples in a rare pediatric cancer. And this is going to be starting in organoids, but ending up with giving drugs to patients. This is like really exciting stuff. So when I joined the lab, I looked at all of this and I'm like, what can I do here, right? And if you take a step back, there's really like a hierarchy where we're developing methods for efficient cell killing, going into local tissue response, but also the samples come from patients. Patients have whole body physiology. They receive lots of treatments. They will receive other treatments after you're done with the sample, and the treatments interact, right? So how is what we're doing at the biological level affecting the patient level? A patient, by the way, looks like this. There's a lot of stuff that's going on. So how do you define good covariates to model what's going on in your tissue? So this is the need, right? We have lots of machinery for fancy sample level, cell level things, but we don't have a lot of good models for understanding patient level physiology and clinical progression over time. And this is where we have the need for a patient state model, and that's what I'd be hoping to build in my next 3 years here. So the idea is we want a good representation of a patient state, whatever state means, and we want to learn that from the full clinical history that we have of the patient across all this rich and growing data modality. And we want to make it easy for other people to eventually build on the covariates we discover for their downstream methods, right? So how do you train your patient state? Put yourself in the shoe of a clinician. You have a patient who comes in, you look at them, you give them a diagnosis. In the cancer context, usually this comes with some imaging of where the tumor is. You do some genomics, you treat them with drugs. And at this point, you have a couple of questions. Will the patient respond? If the patient responds, when will they relapse? And where will the relapse occur, right? So the first insight here is that an informative patient state needs to enable predictions. And predictions span across a wide range of clinically relevant tasks. Now, this is hard, right? How are we going to write down every single question that a clinician cares about and turn them into a prediction task? Well, it turns out you don't have to. Because the answer to a lot of these clinical questions are implicitly encoded in electronic health records. You don't have to believe me on this. Let's look at this patient, right? Will the patient respond to treatment? Well, we look at their next scan. If the scan shows the tumor disappeared, great, they responded. When will the patient relapse? You take a sequence of scans across time, and this is common in the cancer setting because we regularly monitor patients, and you just time the sequence of scans until you see the tumor recur. And you also found out where the tumor has recurred, right? So really what we need to do is to train a self-supervised model to predict electronic health record events. And if you have sufficient number of events across data modalities, you can begin to capture some notion of patient state. Here is one patient that I plugged from MSK's internal data. This is a female colorectal patient. Colorectal cancer patient. And you can kind of see the pattern that I pitched to you in the cartoon at the beginning, right? Where the patient undergoes a period of initial treatment and goes through remissions with several scans followed by recurrence. The good news is we have a lot of these patients, like 66,000 patients. This is probably the largest data set any researcher can get their hands on at the moment if you're not working at a large company. This comes with almost 90,000 tumor sequencing because sometimes we sequence multiple times the same patient across primaries and mets. 360,000 treatment events, 1.8 million radiology scans, 5 million labs. You can read for yourself. So the really exciting part is this week I learned that we might have 500,000 of these people. So keep posted on that. But what we can begin to do, right, is imagine building a model where we take all this high-dimensional, multivariate patient clinical history and shove it into a model and ask the model to predict future events. And that's indeed what we have done. This is a lot, but I just want to highlight 3 design decisions at the high level. The first is this patch idea in purple. And the intuition here is basically we don't care whether you're coming in on Monday or Friday because your doctor is overbooked. But what we do care about is within the span of a week or 2 months, whether something has happened to you, whether we gave you this drug, whether we found this tumor site, right? We take this set of events across a patient's history and encode it into a single patient patch embedding vector. And this gives us a flexible way to summarize various number and types of events, including missingness. And then encode that with time and have an autoregressive model, which is the same as ChatGPT, look over your history to make a single prediction of your patient state. So the patient state vector in gray here, you can think about as the most succinct summary we can derived from compressing your entire clinical history up until this point in order to perform multitask prediction. And the multitask prediction we're doing is literally everything that you can do on the data. So we do survival, we predict 330 treatments, we predict tumor presence at 9 sites, 720 gene alterations. There's some caveats here, and around 40 labs. And we also build in relevance attribution because the first thing the clinician asks is what drove the model to make this decision. This is still early days, but let's go through some preliminary results. This is what the model's world looks like. It's messy, I know, but let's break it down. So in red, you have real data. This is literally from EHR records that we've printed. And here I've selected 4 tracks: BMI, tumor site, treatment, and gene alteration. It's not very important. But in blue, it's basically the model predictions overlaid across the data. The model sees everything to the left of a particular day. It makes a prediction. And if we have real data, we update the model with the real data. And then the model makes the next prediction. And what you want to see is the red and the blue basically overlapping. And here, kind of like just as a vibe check, we do okay, right? And in between where there's no data, the model starts to make some interpolations. And we can talk about that down the road. One thing we get out of this for free is dynamic prognosis. This is kind of cool because up until like very recently, when people make a prognosis model in the clinic, they take features and they compress it across time. So the question you ask is, given that you've ever received a chemotherapy, how does that affect your survival? That's kind of like a reductionist version of the world because we know the order in which you receive chemo versus immuno, which one comes first, affects the efficacy of the other therapy. And here we can basically run the model on a daily basis and have a time evolving view of how at risk you are. And just to build some intuition, we see that here the patient enters a period of remission where they're found to be tumor-free, and the model kind of drops the survival hazard over time until a new finding emerges, right? So what we can do is look across a cohort of patients, take static time slices, 6 months, 1 year, 3 years, 5 years, and basically take the instantaneous model estimate of your hazard, and then go back in and rank all the patients across different cancer types and look at how the model is doing. I just want to emphasize that this is a really hard task, right? We're asking a model to rank 65,000 patients across 10 years of their lifetime or however much we have them for. And the model needs to do this perfectly in order to do well within each subset, which it doesn't know. And at 6 months, if you're estimating the death of a patient, this is integrating over future recurrence and future treatment, which the model also has not seen up until this point. So like, this is pretty hard. We do really well on this. So I'm sorry for the small font, but the bottom, you see this orange line, that's 0.6, 0.5 is random, 0.7 is considered pretty good for the field, 0.8 is exceptional. And across common cancer types, separated by staging, we do really well within each subset. At 1 year, we can use the model hazard score to stratify within the cancer type, and you can see clear separation between the risk quartiles. So that's also really exciting. We can also plot this across the different cancer types since we're training a pan-cancer model. And here you can see that we're actually achieving pretty consistent performance predictions across cancer types. And there is a 10 times data gap from the left of the plot to the right of the plot. This is exciting. Yeah, I think I need to check this, but like for a couple of these, I'm pretty sure we're doing like the best out there. Okay, so that's survival. Let's talk about treatment. What we want the model to do in this case is, I think the patient received the osimertinib treatment. And what we want the model to do is exactly what's happening here, right? That the model slowly increases the probability that's assigned to a particular treatment before the clinician gives the treatment. And this is sort of intuitive if you think about it, because there's time lag between when you get your last scan and when your primary physician or your oncologist has time to see you and give you that treatment. But all the information is kind of already there. So if the model fails to anticipate the treatment, it's going to do something like this, right? It assigns a low probability, it sees the treatment in the data, and it's like, oh, okay, this patient is on drug. I guess I'll just like keep giving the patient the drug. But if the model successfully anticipates treatment, it will slowly kind of rise the probability over time as you see more events. And this will kind of meet when the doctor actually gives the patient the drug. This is how we do on 3 cancer types. It's not amazing, but we're starting to see kind of like this kick up in treatment probability over time, and it's something that we'll keep looking into. Last but not least, explainability. So the first question you get when you show a model like this to a doctor is, so what is the one lab or the one decision that's driving this model? And this is kind of interesting because the whole idea of deep learning model is you're building a complex nonlinear system, but people really, really, really want linear explanation. So we give it to them. I built a dashboard, which unfortunately I can't show you today, but essentially if you click on every single of the treatment events that the model decides, here we're clicking on a radiation therapy treatment, the model can give you positive and negative attribution that tries to explain which of the input variables is driving this prediction. And here, when the patient is putatively receiving a radiation treatment, according to the model, we see positive attribution flowing towards this time point where we're discovering a lung recurrence. This is a lung cancer patient. And negative attribution flowing towards the previous period where the patient was deemed to be cancer-free according to the data. Okay, let's zoom back up, right? Why are we doing this now? And why do we care about this? So from like early 2000s, there's a congressional mandate for hospitals to adopt EHRs, and there's all sorts of financial incentive. And this pretty much happened, saturating in like 2010s to 2015. For a while, all this EHR data is sitting there. Nobody's really doing anything with it because this is really hard to work with. But starting from like 2-3 years ago, there's an advancement in NLP that enable people to go back to free clinical text that like the doctor wrote down or typed down to extract basically like structured features. And now with large language models, people are kind of directly taking starting to take clinical conversations and plug those into structural features. And on the other hand, you have these long context multimodal model advancements that enables you to start to reason over this complex data. If we go back to the beginning, where I asked you how we can contextualize this patient for someone's analysis, I want you to think about a problem that's larger than this. If I give you this patient and ask you who is the 50 most similar patients in your entire hospital, how are you going to begin to find them? I think that's what's really exciting for building this kind of like patient foundation models. And a lot of people are slowly realizing this and going towards this direction. So hopefully we will get there. The goal is to build a large pan-cancer clinical trajectory model that can reveal clinical subtypes, do risk predictions, and downstream, maybe we can do something interesting with discovering therapy combinations. This is This is my lab. Thank you. Happy to take questions.
I have a lot of questions, but I'm only gonna ask one.
Okay.
How do you deal with the fact that like the landscape of treatments changes all the time with like new drug approvals and like you're training on 2012 data versus like 2020 data, like therapies don't even exist, so like your model probably trained kind of on both. So
Yeah, that's great. Right now we don't. Right now the model just learns to clone behavior of the clinician. So this is basically weighted by how much of each case is available in the data. But because we have this nice thing where we're predicting hazard, what you can start to do is imagine tying that component together with like some sort of reinforcement learning setup. And then we can start to incentivize cases where the model predicts a treatment, the patient is given the treatment, and then the model predicts correctly that the patient has like a higher odds of survival. So this is like something 1 year in the future, but yeah, good question.
With the explainability thing, if you mentioned that you can kind of that is it with the line-like kind of explainability thing? But my main question is, have you checked whether these things, the explanation actually makes sense?
Yeah, so that's a good question, and the answer is basically all this explainability stuff is a beautiful lie, right? You have a nonlinear model, and what you're asking with explainability is A, I want to linearize the effect of an input, and B, I want to explain the effect of this input conditionally independent of all other combinations of other input. This is like basically impossible. What we want to do with the explainability, very frankly, is to give the clinicians a way to kind of click around, build intuition of the model, so that it helps them to start to like use it and understand how to use it. Yeah, so there's like Lime, there's SHAP, there's various things. They all have severe limitations, but yeah, it's the best we've got so far. Was there one at the back? Yeah.
So, as you're probably well aware, the EMR has a lot of biases because it's originally intended for purposes of billing and tracking insurance. How do you kind of safeguard this type of work from those biases? So, for example, if somebody comes in and they have some type of fire treatment, right? The EMR that you see doesn't really account for whether they were taking some other medication. For example, also, if there's like biases in how frequently patients visit, like there's more entries for that given patient versus someone else who maybe just happens to come less often to these visits. So have you given any thought to biases?
Yeah, keeps me awake every day. So the answer is we try to avoid using things like ICD codes, which is like infamously skewed for billing. And at MSK, we have different things like, for example, the tumor registry uses a different system of classifying diagnosis that's not dependent on the ICD code. So you have ways of like trying to reduce biases there. What you ask with regards to like external treatment, yeah, this is something we suffer from because we're a referral center. Yeah, it's frankly a little bit hard to get around that. Imagine if one day you have like all of the EHR of, I don't know, like a universal healthcare system, then that would be really nice. But we don't have that, so we do the best we can.
Nice talk. I was curious, you predict hazard ratio, and you also mentioned at one point, the order in which you get different therapies, like immunotherapy or vice versa. I'm curious if you thought at all about using your predicted hazard ratios and then perturbing your sort of prognostic recommendations for a patient to see if you can discover previously unknown correlations time-wise. So, for instance, a 1 week versus 2 week versus 4 week lag between different therapies, or different therapies. Like, for instance, there was a nice paper a couple months ago showing that the time of day in which you get immunotherapy, you get in the morning versus at night, makes a huge difference in outcome. I'm curious if things like that, is there anything
Yeah, good question. Maybe the second PhD, I don't know. We're thinking about this. Yeah. Cool, thanks.